I'd like to welcome you all to the Wigner lecture today. We have a very distinguished speaker, Sir Michael Berry, who's going to be giving a talk on mathematics in his areas of physics and mathematics. Just wanted to tell everybody and remind everybody about the Wigner lecture. And the lecture itself is honoring Eugene Wigner, who was a giant at this laboratory and what made a lot of the direction of the laboratory, set it off early in its history. When we started this lecture, it was timed with the 70th anniversary of the graphite reactor reaching criticality, and that was in November 4th of 2013. And so it's been 5 years since we've had the lecture. We've had about 25 lectures over those 5 years. And this year is another special year for the laboratory because it's the 75th anniversary of the laboratory. So this is a really nice lecture, our first lecture this year to kick off our 75th anniversary. This series of lectures, as you know, is organized by the corporate fellows, and they're the ones who host the lecture and select the lecture. So we're really pleased with the corporate fellows taking on this role for the laboratory. The goal of the lecture series is to invigorate scientific discovery. It's to spur technological innovation and to initiate productive science policy debate. And I think that having some of the lectures that we have, including Dr. Berry here, is just great to get people talking about new areas of science and bringing that type of science into their work as they go forward. Again, this lecture honors Eugene Wigner, who we all refer to as kind of our patron saint. He was a chemical engineer by training, but he said that he was a physicist by inclination. So we that are chemists, we have to give people up every once in a while, but that's okay. We like physicists. He was viewed as the founder of the field of nuclear engineering. Has a very bright man who had a lot of impact in a lot of different areas of science. He was a role model for coupling basic and applied science, and that is a hallmark of this laboratory amongst all of the national laboratories here. This is something that he started, and we continue to this day. He was the director of Oak Ridge National Laboratory, which was then referred to as Clinton Laboratories from 1946 to 47, and of course he won the Nobel Prize in Physics in 1963. So today, Professor Berry is joining us to give his lecture. He started in 1960, Eugene Wigner published a paper on the unreasonable effectiveness of mathematics in the natural sciences, and today Professor Berry is taking kind of a riff on that as a starting point for his lecture. He's a mathematical physicist at the University of Bristol in England, where he is the Melville Wills Professor of Physics Emeritus. He's focused on exploring what he calls the borderlands between physical theories, between classical and quantum, between rays and waves. He is well known for his work on the physics of waves and quantum phenomena, but his interests include optics, tidal bores, and magnetic levitation. Some of his papers are just really interesting. I've enjoyed looking at them. He received his undergraduate degree in physics from the University of Exeter in 1962, his PhD in theoretical physics from St. Andrews in 1965. He was knighted in 1996, and so he is in a very rare air of our lectures to have a knighthood. His title today is called Making Light of Mathematics, and I'd like to really welcome you warmly to Oak Ridge to join the long line of distinguished lectures that we've had for the Wigner Lectureship. Thank you.
Thank you. What an honor to give this talk in a series celebrating Eugene Wigner. Among the many talents of this great scientist, perhaps his main talent was the way he perfectly fused mathematics and physics. And that's going to be my theme today. Physics and mathematics evolved together, and they remain intimately connected. Now, sometimes it's important to distinguish them as separate intellectual activities. We have universities with mathematics departments, we have physics departments, but in our everyday scientific practice, it can sometimes be hard to tell them apart. Peter Atkins, in one of his books, put it beautifully. I'm quoting, "Determining where mathematics ends and science begins is difficult and as pointless as mapping the edge of a morning mist." Now, I spend my life wandering in and out of that mist, so please don't waste time wondering whether this is going to be a physics talk or a mathematics talk. Now, for this occasion, I judge that a technical talk is not very suitable, but that doesn't mean that the presentation will be elementary. Some of the ideas will be fairly sophisticated. Now, I'm going to show many pictures, and this needs some explanation. In Wigner's papers, certainly his standalone papers, the ones I've looked at had no pictures at all. At least I didn't find any. If there are pictures, then they are few. Maybe he drew pictures to help his understanding or while talking to people, but didn't include them in his papers. Maybe not. Some very creative, great scientists seem to be not particularly visual, even when they say that they think in pictures. Even when their science is geometric. Paul Dirac is another example. But many scientists are strongly visual, and their papers do contain many pictures, mine do, especially nowadays when it's so easy to create pictures. Now, we know that a picture is worth 1,000 words. But we also know that an equation is an economical encoding of infinitely many pictures. But economy and worth aren't the same. And the compactness of equations can make it hard to comprehend their content, and pictures can help. Now, nowhere are the intimate connections between mathematics and physics more immediate than in optics. With our eyes and with our brains, a fact I'll return to at the end in connection with Wigner's unreasonable effectiveness of mathematics, with our eyes we can see directly through physical phenomena, almost to what I'm tempted to call mathematical phenomena. And I'm going to show you some mathematical phenomena and their counterparts in light, turning mathematics into light, as my title suggests, or is it the other way around? So let's get started. Physicists' working clothes. Here we are. Let's start with some mathematics that I hope won't intimidate you. 1 + 1 = 2. Nothing could be simpler, as we'll see later. Now it applies to two candles or two flashlights. Their intensities add. But flashlight is messy light, and for pure light, intensities do not add. 1 + 1 does not equal 2. Instead, waves add, wave amplitudes, with the additional property, relevant, central to this non-applicability of 1 + 1 = 2, that they have phase. Phase specifies the stages of anything that oscillates, the moon's shape over a month, for example. Now, for two waves, the differences of phase cause interference. So you have two pure waves, and their intensity can be, each of them has intensity 1, and 1 + 1 can be anything between 0, which we will discuss later, and 4. Perfect blackness, 1 + 1, intensity = 0. So this poses a problem. Once you know this fact about light, why are two flashlights twice as bright as one? There's apparently, I've never found it, a paper by Lord Rayleigh with this title, Why Are Two Candles Twice as Bright as One? Well, it's because I said the light is messy and the phase varies rapidly and randomly, far too fast for us to see these variations, and it's the average. And the intensity averaged over all the messiness is 2. Now, this took a long time to understand, and it was Rayleigh who understood it, but now it's central in a quite different area of physics, which is quantum physics, where it's called decoherence. So recovering 1 + 1 = 2 is actually quite sophisticated if you think properly about light. Good. Okay, well here's some interference near a line of focused light. The phase difference is increasing as you go in. Now, another word for focusing, which I'll use again and again, is acoustic. It refers to focusing more general than just the point you get at the center of a lens. It's the surface in space, or the line in 2 dimensions, along which the rays of ray optics are focused. So I want to spend some time on this. Here's a rainbow, and you see inside lots of superluminary additional rainbows, and these are interference fringes. Thomas Young, when he was teaching us with his 2-slit experiment, interference, that light is a wave, something that Newton didn't understand 100 years before, he used these rainbows as an example. Well, here is an example where you can just see one supernumerary rainbow. There it is. There's a secondary bow there. That's a different thing. It's one more reflection. But I'm showing you this because this is an ironic picture, because here's the house where Newton was born. It shows you, well, as iconic colours of the rainbow, it shows you something he wasn't able to understand. Okay, well, what are these fringes? Well, they're interferences between 2 rays that emerge in the same direction inside the rainbow. Here's this line of intense light, the concentration, but inside there's also light, and you get 2 rays, and it's their interference that you're seeing inside. If you make a graph of the deflection, as it depends on where the sunlight hits the drop, this is sunlight and here's a raindrop, then you've got this minimum, and that's so mathematically, it's another piece of mathematics. It's a 2-to-1 map, because 2 rays come out in one direction. But when they coincide, in mathematical terms, that's a singularity of the map. So this term has a direct applicability in a rainbow, and that's a caustic. If you rotate this about its symmetry, there's a cone of bright light emerging from any raindrop, and you, on the ground, looking up, see, brightly lit, all those raindrops on whose cones your eyes lie. So there's some little mathematics to do with rainbows. Here we are again. Here's something else. You've all seen sparkling water. And you know or can immediately understand that these images are places where the wavy water just has the right slope to reflect sunlight into the eye. It's a many-to-1 map from the sun to the eye via the water at a given instant. If the water was perfectly still, you'd see just one image, a 1-to-1 map. Good. Well, what happens as time passes? Well, the water waves, and these points move around, and they coalesce and disappear in pairs, and they're born in pairs. And what's happening there is that in the space above the water, the reflected light forms complicated caustic surfaces. You don't see them, you only see the light that's passing through your eye. But when one of those surfaces crosses your eye, then that's a moment called a twinkle, where two of these images disappear, or 2 of them are born. So here's a picture of that. if you were here, you'd see one image. If you're here, you see three. Here you see five. And these are the caustics. I didn't draw them. The rays themselves draw them. It's the envelope of the family. And it's the rapid succession of these twinkle events that give rise to the sparkling appearance of water. So the sparkling appearance of water is a result of the singularities of a many-to-one map. That's mathematics and its light. Okay. Now, the mathematics that describes this type of phenomenon is called catastrophe theory. The name comes from something, a different, irrelevant application to do with collapsing of bridges and the like. It describes what we call natural focusing. You know, this wavy water isn't a lens designed by a lens maker, and these caustic lines are not points that you'd get in an ideal lens. So you want to talk about that. And these caustics in light are the physical embodiment of this mathematics. And I'll now talk a little bit more generally about them. As I say, they're focal lines or surfaces of families of rays, and from a wavy lens or mirror. Now, they're the rays, and you see the caustics like I've shown you. Now, caustics are holistic things. You have to know this. No single ray can form a focus. You need a family of them. It's a property, a holistic property of the family. And what the mathematics does, it classifies these according to the number of dimensions they have. Not quite. It's the co-dimension, the number of dimensions you need to explore it. Now, the simplest is called a fold. It looks like a fold. It gives the illusion of a fold. This is a line in the plane, like the rainbow, a line in direction space. You need one dimension to find it. Next to that is the cusp. Now, it's not obvious. It's the only singularity that's stable, that's natural, that persists in its form if you change the conditions. This has codimension 2, so in 3 dimension there'll be a line cusp, a piece of paper like this, like that. You've seen these. You've seen in your coffee cup this curve. There was a professor in Bristol that Malcolm Stocks will know, and he was invited to the house of one of our colleagues, Boles Durfee, who used to visit here, and he sat on a windowsill that had just been painted, and the imprint of his backside on the paint when he stood up was exactly this shape of curve. It was a great moment in the history of this distinguished professor. Okay, I have a friend. She's a sculptor, an artist near Bristol, and she makes these, what she calls light catchers, and you see cusps everywhere. Good. If you're walking at night in the rain, and does it rain here? Not today. Anyway, and there are raindrops on your glasses, which are not as clean as you think they are. These are little irregular water droplet lenses. If you look at a distant street light, its image is distorted exactly like this, and you see lots and lots of these cusps. They are naturally occurring caustics, and there's some I make in the lab. Now, you go to 3 dimensions. I'm not going to emphasize this much. I'll talk a bit about it. There are 3 types of singular point. It's far from obvious. You needed the mathematics of the late 20th century that this is one of the only 3 types of structure you can get in 3 dimensions. You need a surface to see this. And here is one, never mind about the names. Now, if you shine light through a piece of irregular bathroom window glass, if I could have brought my nice bright green laser pointer on the plane, I only have carry-on, I would have done it in person for you. Then you shine on a screen, this of course is a red one, and you see these lovely patterns. You see cusps, you see the little bits of hyperbolic umbilics, here they are, and if you look closer, you zoom in, you can see these little triangles. These are what I just called elliptic umbilics. So all of these, this zoo of forms, which we studied in great detail in the 1970s when we were aware of the mathematics, thereby completing the ancient branch of physics to do with focusing of light, several hundred years old. We saw all of these singularities. Great fun. Here's a practical example, a very interesting, beautiful example. In 1976, Mars passed in front of a star. That means it blotted out its light for a few minutes. And if you look at an observatory, which in this case an airborne one, in the right place, you would see this light diminishing. and it would switch off then switch on again a few minutes later. But not quite, because Mars has an atmosphere, and the atmosphere bends the light and focuses it onto a focal line, and if you've got your observatory in the right place, you expect to see in the middle of the disappearing light a little flash as this passes you. Okay, and you can work out what the structure is of the caustic. It's some spun cusp which is not relevant, but this line you should see passing. And they did see it. Here it is. Now, this is the time, 6 minutes or so, and here's this central flash. But this focal line is an unstable thing. It wasn't in the library of shapes that I showed you. A line into a point in 2 dimensions was not in the little library of forms. You need a lot of optics, careful design to produce that. So you actually expect to see some fine structure caused by the fact that Mars isn't a sphere. It's an ellipsoid. And that's enough to break the symmetry. And in fact, you can predict theoretically that this unfolds to this shape. So you expect to see whatever this would reveal as your telescope crosses it. Well, this is what was predicted. This is the path of the telescope through this structure. You expect to see the smell this cusp, and then to see these 2 folds. And when they zoomed in, this is what was predicted. This is now seconds. When they zoomed in with their data, that's what they saw. It's a fantastic example, putting it in an abstract way, of a stable singularity resulting from a symmetry breaking perturbation. Symmetry breaking being one of the great themes of theoretical physics of the last decades. Good. So here you are again, bathroom glass. And of course, you see, and I started with this, you see lots of interference, you see lots of waves. Each of these types of geometrical caustic is decorated, it's clothed by its characteristic wave pattern. And I want to talk about this one first, decorating the fold. It's the Aries, Airy, the astronomer royal of 200 years ago, his rainbow wave. That's the intensity. Good. It applies to many places. Here's a moving ship. The V shape, you've seen this, this V shape behind a moving ship is actually a caustic of the rays of the water waves. It's a very general phenomenon. It always has the same angle, 19 degrees or so. And so crossing here is an Airy function. Now, I've shown you how you can see these undulations decorating rainbows if you don't have too much decoherence. I didn't say this. You see more rainbow fringes when the raindrops are nearly all the same size. But you can also experience it in water. I did recently, if you're on a small boat and a big boat goes by, its V shape will eventually reach you. It'll take longer than you think because you see the waves, but the wave velocity is twice as much as the group velocity. So it's twice as long as you think, but it will reach you, and you go up and down in your boat, and then you're feeling in your body the undulations of the Airy function. Okay. Near Bristol, we have a number of examples of a phenomenon of a tidal bore in the world. It's the incoming tide, but develops into a wave with an interesting structure. This is focusing in space-time. That's an Airy function. And there was this poem by John Keats. It was a kind of anti-science poem. He was kind of silly. I mean, he was too young. He died too young. And he said, "There was once an awful rainbow in heaven." And he used the word awful. It means awe-inspiring. Well, that's correct if you realize that also the Airy function, this course, is involved in understanding tsunamis, which are the most destructive of all natural phenomena. Very good. So now let's go on. The waves that decorate a cusp, this nice pattern. You do see these little pairs of black points. I'll show them more carefully in a while. They are zeros of intensity, and you can dimly see them there, but you can see them much better with a computer. You can plot the intensity of these waves, and we'll come back to this picture later. Here are the little pairs of 1 plus 1. Actually, it's 3. It's 1 plus 1 plus 1 equals 0 in this case. Let me talk about something else for a little while, then come back. I want to talk about another kind of mathematics. Here we again. Here's this way, the function. Airy couldn't calculate this wave very well. He could just calculate this little narrow region here. It very often happens in physics. You have a theory and you can't calculate it exactly. But we use approximations. And common kind of approximation is infinite series. You guess something. Suppose the something you want to eventually is going to be 1. But you can make a crude guess and you get a half. Then with some improvement, you add a quarter and then an eighth. Well, you can see what's happening: 3/4, 7/8, 15 16ths. This is a convergent series, and it represents 1. This is extremely common in physics. We guess something on the basis of a little simple model, correct it, and hope to home in on the answer. But often series diverge. I don't know if you've seen it, went viral a while ago. It's 1 plus 2 plus 4 plus 8 plus 16 is -1. Really? 1 plus 2 plus 3, this went viral on the internet. I've been using it for years. -1/12. I have, my wife and I read in bed, different books usually. I was reading, suddenly she said, "What's that?" And it was a bookmark given to me by the software company Mathematica. You spend thousands of dollars over the years, and they give you a bookmark as a freebie. and on the bookmark, there was this little formula, and she said, "What's that?" Now, she grew up in Romania and learned mathematics much more sophisticated than I learned the biology, which is what she does. And she said, "It's nonsense." I said, no, it's a zeta regularized sum, blah, 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 blah. And she said, "Well, it's nonsense. It's all positive. How can..." Anyway, to cut it short, a robust domestic disagreement followed. And there's an argument which I won't give, how this can be interpreted to give meaning. You know, I mean, lots of mathematics was meaningless to people before the genera. I mean, the idea, if you wanted to subtract 3 from 2, we say you get a negative number. But if negative numbers aren't in your vocabulary, it's meaningless, so increase. So they're interpreted. But even this is not what usually happens in physics. What usually happens in physics, and Stokes with the rainbow integral, he had an infinite series which is of the type we regularly find, in which the corrections do get smaller. That's great. It's a bit like this: 1 plus 1/10 plus 200th plus 6. It looks as though the terms are getting smaller, but eventually they don't, actually. Eventually they get bigger. These are called asymptotic series. This has a number, and here this is what happens if you add more and more terms. It looks as though it converges. No, alas, in the end it diverges. There's a huge amount of mathematics still being developed now, going back to Stokes, to do with infinite series, and it all started with the rainbow. So it's mathematics and light once again. Now, I told you when I began, 1 plus 1 equals 2, nothing could be simpler. Excuse me, yeah. No. Well, nothing is simpler, and I'm going to talk about nothing for a while. Much ado about nothing this will be. The complete destructive interference I've already mentioned several times. So I've shown you this already. Here are these 2 places of 0 and the wave that decorates the cousin. If you look carefully with your glasses in the rain, you can just about see these fine details unaided. Okay. Well, what's happening there, you can see more clearly if instead of the intensity of the wave, you look at the phase. We can't see that directly. We see the intensity. With interferometry, you can measure the phase, and it varies from place to place. The natural way to represent phase, which is a periodic thing, is using color, using hue. You go around the color circle. And the zeros, when there's no wave, you don't know what the phase is. It's like asking, what's the time at the North Pole? All the times come together. And so it is, if you plot the phase, given color, it's like red and green is a trough, and in between you get the colors, then these are places where all the colors come together. Now, this is a very general phenomenon in waves of all kinds that my colleague John Nye and I identified in the 1970s. For example, you take random waves, nothing to do with rays and caustics anymore. you add waves, all of the same wavelength, going in many different directions, and you get a nice intensity pattern. This is color-coded, bright here with some zeros. Look at the phase, and every zero is a place where all the phase colors come together. This is 2 wavelengths square. It's fine structure on the scale of the wavelength, which people used to think didn't exist. There they are. So you see this in many places: laser speckle, the section of black body radiation that pervades the universe, electron waves and a chaotic quantum dot. This is physics of waves on the very finest scale. But it's in 2 dimensions. In 3 dimensions, these are lines. As I'm speaking to you now, the air is filled with a forest of phase singularity lines of sound, threads of silence, passing across your ears too fast for you not to hear them. Okay. Well, we knew they could be curved and closed, but there's something else that happens in 3 dimensions, much more interesting. You could ask this question: could these lines be knotted or linked? Well, that brings in more mathematics, knot theory. Okay, in particular, we first found knots that you wind on a torus, a donut. You go round n times one way and m times round the other of this donut and join together. And here's some other examples. These, if you would find them in light, which we predicted you can, would be lines of darkness. By the way, knot theory, this is a classic paper from the 19th century. The first 7 orders of knottiness, it says up here. They're not, there are some mistakes in this, actually. Tate, following an idea of Kelvin that they didn't know about atoms. They guessed they might exist. They didn't know about their structure. But they wondered, how can the atoms of a given chemical element all be the same and different from another? And Kelvin had this fantastic, brilliant, wrong idea that maybe each atom was a different kind of knot in the ether. It's wrong, but it was very productive because it stimulated Tate to invent knot theory, still incomplete. I'm trying to remember what a mathematician wrote on a napkin in a restaurant. I'll try to say it. A knot and another knot need not be the same knot, even though the knot number of the one knot and the knot number of the other knot differ not. But if the knot number of a knot is the knot number of the not knotted knot, the knot is not knotted. Okay. Well, we found that you could make knots in light, and here are some that we predicted: threads of black light, knotted nothings, and they've been seen in holographic holographic grating experiments. Here are some knots and links, and my colleague Mark Dennis and I did the theory, and a group of Miles Paget in Glasgow did these rather tricky experiments, seeing nothing. You know, if you go, you all know, if you go into a lab where there are laser optics is going on, you can't see the light except where it hits some dust. But in this, in these experiments, in the light that you can't see, there are lines of zeros that you even more can't see. But if you put suitable screens in the way you can, and you build it up bit by bit, and they found sort of lovely knots later on, more complicated knots in experiments. Right, something different. I talked about interference. I'm going to talk about extreme interference. You know what a diffraction grating is. It's lots of slits in that transmit light in narrow beams through something opaque. You shine light on, and you ask a question. N slits. What's the light at some point P far away? Well, it depends on a number, on a spacing of the slits squared, divided by the wavelength, divided by it's a number. Now, what was interesting, and not part of classical optics, as it's not quite the regime that you use diffraction gratings in, is that this wave, of course it's the sum of the waves that come out of each slit, little wavelets. But and so if you geometrically add these little intensities with an angle that represents the phase, there it is, then it turns out that the phase angle you start with is x. The next one is 4x. The next one is 9x. X times n squared. Add them all up. The pattern you get depends very sensitively on x. It's something, mathematics, called the Gauss sums of number theory. I want to show you some of these patterns because they're really remarkable. And analysis is even more remarkable. This is interference of many, many thousands and thousands of little segments according to this rule. Depends on the x, 10,000. I call these things curlicues. Look in the dictionary, a fantastic curl or twist. So here is something small, square root of 101 minus 10. Well, there you are. So it starts to coil up, and then uncoils and coils again. You realize you get a coil of coils. After some time, a coil of coils, along it goes. A lovely structure. What about 1 on pi? That's a nice number. There you get this horrible spidery thing. What about the golden mean number? Square root of 5 minus 1 over 2. Well, you get a Christmas tree. And there's an amazing theory of these patterns. And for typical numbers, not these special ones I've showed you, it turns out that the curlicues are a kind of arithmetic microscope. The more you zoom in, the more you know about x. And it turns out that in the mathematical theory, for almost any x, the curlicues, if you zoom in and look at different scales, look like the curlicues for almost any other value of x. It's a kind of marvelous thing. Now, this is hard to see experimentally. You can, in principle, and to a very limited degree in practice. But here's something where this arithmetic appears in something discovered long, long ago and only understood relatively recently. Again, diffraction rating, something called the Tolbert Effect. Here's light coming in, and you're looking in some plane. Now, what Tolbert did, he had this grating, light coming in, a magnifying glass, he looked and could see the slits. You could move away, they go out of focus. But suddenly, they come back into focus again at some distance and multiples of it. It's the same number. It's the spacing of the slit squared divided by the wavelength, and it's the distance and multiples of that. Okay, very good. Then in the 1990s, it was realized that suppose you have a fraction of that distance, p over q, 2/3 or 1/2 or something, then what you get is the denominator, q superposed images of the grating, superposed in a way, depending on interference, that depends on the arithmetic of p and q. Again, it's the Gauss sums. And for the simplest grating, black stripes on a transparent plate, so you just see these little white bits coming out. Here's the intensity at 0, Tolbert distance, it repeats. But in between, you get these interesting patterns, 1/7, 3/5, 7/9, and so on. I can't resist showing you, there's one equation which you develop and develop, which gives you the understanding of this. It's -1 to the n squared is -1 to the n. Why? Because -1 to the n is, it's 1 or -1, depending on n is even or odd. But if n is even or odd, n squared is similarly even or odd. Just that, but deeply buried away in the mathematics. But then you want to ask this question, well, it's okay for integer p's and q's, but suppose you have some irrational, 1 over √2 of this distance or something. Well, then you get more mathematics. You get fractals. You've heard of fractals. They're structures, they're infinitely fine structures, which can be represented, they're geometrical patterns, as though they have a dimension that isn't a whole number. So a curve, smooth curve, has dimension 1. There are wiggly curves whose dimension is between 1 and 2, depending on the wiggliness. And when you get to 2, you're filling the plane. Okay, well, it happens here, at least down to the wavelength scale. So they're fractal curves. The prototype example given by Mandelbrot was the coastline of a country, England, for example, because you zoom in and you see more and more structure, and the length of the curve depends on how finely you sample it, unlike a ideal smooth curve. Well, for Tolbert fractals, it's more complicated. The dimension across the light is different from the dimension along the light. So here we are, here's the light, and if you look across, it's 3/2. If you look along, it's 7/4. It's more wiggly, nearer to 2. But there are also these diagonal lanes where it's less wiggly. And all this we've seen in experiments. And you put it all together, you get a surface above this plane, And the intensity of the surface, I call them the mountains of Tolbert. It's the marriage of Tolkien and Mandelbrot. You get this fractal landscape with dimension 2 3/4. Okay, very nice. We in theoretical physics are never more happy than when we find in one area of science something closely, pretty identical in its structure from something in a quite different area. And in the 1990s, again, something was discovered in quantum mechanics which we realized was actually structurally identical to the Tolbert effect. Here's a dictionary. In the Tolbert effect, you've got distance from the grating. In quantum mechanics, it's time. You've got a wave equation for light, relevant one, and in quantum mechanics, it's a Schrödinger equation. So these repetitions in the Tolbert are revivals in quantum. And I want to show you that. Because you get some nice pictures and it's instructive. Particle bouncing back and forth on a line. If it's a classical mechanics particle, this is space, and this is time, it just bounces, 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 and travels, nothing surprising. Here's a quantum particle, and I'm looking near the beginning, long before that revival time, and again, you get something classical. It's a wave, not a particle, so it interferes with its own rear end after it's been propagated, and then it spreads, gradually spreads all over. So this is bouncing, interfering, and spreading. What I didn't say, well, I did say, these fractional revivals, you go halfway, look again at a narrow region, it's as though there are two packets interfering. Here they are. But what happens when you see the whole pattern? It's a fantastic thing. It's a quantum carpet going from 0 to the revival time, and we were surprised to find all these diagonal structures. It's the value of pictures. I give a whole lecture about that, not now. It's the value, and we discovered these lines, and then we were able to understand them mathematically. These structures, some of them, rudimentary versions, have been seen in experiments where you have atoms and you zap the electrons to be far away like a planet, and the electrons go round and round, and as they go round and round, their wave spreads, and then it reconcentrates and spreads and reconcentrates, and these quantum revivals have been seen. Good. So it's a quantum carpet, that's extreme interference. And, here's another little piece of mathematics. Oriental magic mirrors. Probably you don't know what they are. They're cast bronze mirrors about that big, and decent mirrors, not perfect. Here's my daughter, here's some trees outside where I work. The magic comes when you look at the back. The back has deep relief. And if instead of looking in the mirror, here's the front, here's the back, you shine light on it, go out into the sun, and look at the reflection of that light on a surface, a wall or whatever, then on a screen, then what you see, to your surprise, you see a disk, you expect that, but you see a ghostly image of what's on the back. And this was very puzzling. It's a long history, very puzzling when these were brought from Japan to the West in the 19th century. Well, it was quite soon realized that what must be happening is that during cooling and release of elastic stresses and vigorous polishing, the image on the back is somehow reproduced as a relief on the front, too small to see. And like this, I've exaggerated it as the back, there's the front. But it leaves an optics question. How is it that something you can't see when you look produces these rather strong images? They're not images in the usual sense. If they were, you'd have to focus them with a particular position. But wherever you have the light coming in, wherever the mirror is relative to the screen, over a very wide range, you see these quite sharp patterns. Well, it was realized, it's another whole lecture, I'm not going into it, that it's a rather unexplored, very simple branch of classical ray optics where the curvatures are not enough to produce focusing, but they produce concentrations. And the intensity is something called the Laplacian. If you know what it is, you know. If you don't, you don't. But it's a curvature. It's the slope of the slope. Okay. Well, you can test that. You see, here's the observation, and if you can do it on the computer. If you take the relief pattern and calculate this function of it, you do get something which shows a characteristic feature. Every step in this image has a bright side and a dark side. That's what this does. It's in computers, in image processing, it's called an edge detection algorithm. But here it's happening in naturally, and you can test it by zooming in at one of the edges, one of the steps. You smooth up and down, here you do, and then you can digitize and you can measure, and this is only about 400 nanometers, which is why you can't see it, it's below the resolution, but it has this effect. Very lovely thing. As I say, edge detection, it's used in some aspects of Japanese industry. It's called Makyo imaging, wonder mirror imaging, to detect defects in polished semiconductor surfaces. Well, it was suggested that you could see the same thing in refraction. You could have a magic window, perfectly flat, smooth, flat window. It would appear to be. You'd look through it, but if you go out and you shine light through in the sun, then down on the ground would be some pattern. And my two colleagues and research assistant are looking at these to make these magic windows, never details. Now, there are some counterparts. In MIT, Matt Brand produces these wonderful things. Here's you shine this, you have this object. They're different because there you can actually see like a fairground mirror surface, only it's a window. And likewise, there's Mark Pauli in Lausanne. He makes an image of Alan Turing. Well, again, you can see the undulations, but here's a little simulation of what we're aiming to construct. There's quite tricky, my colleagues tell me. It's a regime of fabrication of glass surfaces where the technology has to be developed. It's related to what's called freeform optics, but it's an awkward regime. It's interesting in its own right. So here's my grandson, okay, as he was. You can't recognize him now, they change. So what surface would generate on projection this pattern? Well, it's a tiny, but if I zoom in and magnify, here it is. You have to solve Poisson's equation, and that's a smoothing transformation. So this thing, you can't see it, I've exaggerated, and if it would reproduce, and if you on the computer you simulate, and you see a slightly pixelated version of him. Okay, very good. Last thing I want to talk about, polarized light in crystals. More mathematics. Light traveling in a crystal can oscillate sideways, polarization, in two different ways orthogonally, the polarizations. So here we are, here we have it. Now these polarizations and the speeds with which they travel, the refractive index, depend on direction according to matrix algebra, more mathematics. What's a matrix? Some of you know, but some don't know. A matrix is what the crystal does to light. The algebra is that the matrix times the original light is the light inside the crystal. Now sometimes the crystal light can be the same as the original light. That's a self-reproduction. Then the original light is one of these two polarizations. And these are called eigenvalues of eigenvectors of matrices. But sometimes it could be times a number, the same thing. And that number is, in mathematics, the eigenvalue of a matrix. Now, I want to show you how to see this mathematics with your own eyes easily. Traveling through the crystal, these two waves get out of step. You can interfere them with what we call a black light sandwich. Here's the bread, two polarizing sheets at right angles. It would be black if there were no filling. It's poor person's bread, okay. But we do have a filling. We theorists would like something called a biaxially anisotropic crystal. Well, people like me don't have access to those, but there's something else that we do have access to, and you do too, which you could use, which is the overhead projector plastic transparency foil that we used for several decades to project our talks before we had this better technology. Sometimes, not here, you go into a lecture room and there's an overhead projector, dusty and unloved in the corner, this legacy technology, and we've got boxes of these plastics. Well, this is what you do. You just need a square inch or so, and what happens, what do you do? Well, you look through it, actually, and what you looking in different gazing in different directions, you see the light that's come in different directions. The interference depends on the difference of the speeds. You're seeing contours of constant difference of the speeds. And here you are. And they're centered on these things, bullseyes, which are called matrix degeneracies, places where the two speeds are the same. You do it with white light. This is what you see. There's this black brush. If you go out, there's a sky, not the sun, I mean just a cloudy sky or a blue sky, and you'll see, I'll show you in a minute. What these bullseyes are, they're locally conical intersections of a polar plot of the wave speeds in direction space, something understood by Hamilton in 1830. And these are the cones. Conical intersections are quite common in physics. They're quite fashionable in chemistry, where they describe electron states in atoms, and in condensed matter physics now, topological material science is a hugely developing subject, and a central role is played by these things. They're called Dirac points. That's a bad terminology. They should be called Hamilton points, 1830. There's mathematics, I won't go into it. Anyway, go out in the garden and have one of these in front of your eye, just look, or your camera, and this is what you'll see. And so these are the contours of constant separation of the cones. This black stripe is something called a geometric phase that occurs in lots of other places in physics. I won't go into it. But there's something else. Each of these points here, each of these directions, is a little matrix, 4 numbers. The electric field, 2 components here, outcome 2 components. They're related by 4 numbers, a little 2 by 2 matrix. And all these matrices have an amazing property. They're non-trivial square roots of 0. What does that mean? With a number, the only square root of 0 is 0 itself. With a matrix, A, B, C, D, you can multiply A, B, C, D, and you can sometimes get 0, 0, 0, 0. I give a whole lecture sometimes to students, just with this one picture, to explain many aspects of the mathematics of matrices. Okay, this was nice, do-it-yourself conoscopy. But I had a message from 2 Dutch astronomers who said, look, you can see this through a railway window. Why? Sunlight is polarized. It's another story by the way of making the blue sky scattering by molecules. Polarizes sunlight, although initially it isn't polarized. The waves are random in all directions. The glass of the window is stressed, and that causes it to be anisotropic in a particular way. And like every good scientist, they carry a piece of Polaroid with them and look through it. So you've got a sandwich, the polarized daylight, one piece of bread, their piece of Polaroid, another piece of bread, and the glass in between. And look how lovely it is. They really can see this little bullseye and the black stripe geometric phase. Here they did, here they did. I wanted to see my own. This is mine. The train windows in England are not as clean as in Holland. But still, there it is. You can see beautiful pictures in crystal optics. I won't describe them. It's very visual, very lovely, and there's beautiful underlying matrix mathematics. But I want to finish by talking for a little while about what we've seen. I've told you about a lot of mathematical phenomena. 1 + 1 = 2, intensities of light rays. 1 + 1 does not equal 2, intensities of light waves. 2-to-1 map, rainbow. Many-to-1 map, sparkling of the sun on the sea. Mathematical catastrophes, natural focusing. Infinite series, the dark side of the rainbow and the bright side of the rainbow. If you want to understand that, you get deeply into this very now being developed branch of mathematics. Zeros, dark places where the phase is undefined. Knots of black light. Gauss sums in extreme interference. Fractals in diffraction grating. The Laplacian in magic mirrors, and matrix degeneracies in polarized light, bullseyes. Now, I could have gone on. There's so much mathematics in light and in any area of physics. Now, we are astonished repeatedly to find recently developed and quietly waiting for us exactly the mathematics we need for physics. And of course, much more generally than in this optics I've been speaking about, Riemannian geometry was sitting there waiting for general relativity when Einstein needed it. Matrices, again, were waiting for the main application in quantum physics, fiber bundles, weighting gauge theories, and so on. Now, we are sort of astonished, but really should we be, as Wigner was? Well, we should be delighted, but I don't think we should be astonished. And I want to explain why, because I disagree to some extent with Wigner. We're beings of finite intelligence. We're newly arrived in a vast and inscrutable universe. We know a little bit more than dogs, okay, but from a broad perspective, not much. They can smell things better than we can, but maybe we know a bit more, but not that. Now, we learned a trick in science. Our individual intelligences cooperate, and we can understand more, but still we're limited. We're able to comprehend only those structures that occur in the natural world that mirror our most sophisticated mental constructions. And what are they? The most sophisticated mental constructions of humanity are those of our mathematics. Sometimes the mathematics comes first, sometimes the physics, it's a detail. But what this means is our deepest penetration into the natural world is likely to reflect and be limited by our latest mathematics. And as we and mathematics develop, more subtle features of the universe become accessible to our understanding. So while our species survives, I see no end to this process, as there's no theory of everything. That's ludicrous. So I think that the unreasonable effectiveness of mathematics in the natural sciences isn't unreasonable at all. On the contrary, it's inevitable. Well, it's not unreasonable, but it is wonderful. Now, to finish, I want to quote two small pieces. Maxwell, when he was a young man, the great James Clerk Maxwell, when he was a young man, in his private diary, mused about science and how you understand things in a way that is pretty well a manifesto for theoretical physics, and certainly what I've been describing when you see optics at different levels of description, the ray optics, the wave optics, the polarization optics. He said this: the dimmed outlines of phenomenal things all merge into one another unless you put on the focusing glass of theory and screw it up first to one pitch of definition and then to another to see down into different depths through the great millstone of the world. Now, good, wonderful piece of insight. 100 years later, another young man made exactly the same point. It's the point that we see with our brains as well as our eyes. You don't just look and see all this mathematics. You have to think about it and do experiment. And this was Paul McCartney. The fool on the hill sees the sun going down, but the eyes in his head see the world spinning round. Stop.
Thank you so much. Would you like to join us over here?
Yes, surely. Yes, very happy to do that.
We'll
Just
open the floor to questions. And I'm going to have a hard time seeing with the spotlight, so...
yeah, well, we can't see you, but
yeah.
you can see us.
Yes.
You have to speak a bit loud because I don't hear too well. Oh, here comes the microphone. Yeah.
Skyrmions are appearing a lot, starting with fermion and bosons and fermions, and now into condensed matter physics. Is this a resurrection of Lord Kelvin's knots?
Not quite. I mean, and of course you know it isn't, but it's an evocation of them, I would say. And I'm glad you mentioned that. I mean, there's a huge variety of very interesting topological structures. Some of it developed theoretically in gropings towards structures in elementary particle, high energy physics, now appearing in, as you surely know, I'm just saying, other people, now in condensed matter physics. So it's a development, a part of this topological condensed matter physics, of which these cones are a simple example. I have a colleague, a young guy, who's studying skyrmions, and he even finds them in a branch of solid-state physics where they have a patent for, which I don't understand exactly what it is, a patent for using these skyrmion structure in condensed matter physics as a way of storing data. So thank you for that. Yes, good.
In some areas, like for example plasma physics, we're quite interested in the interaction of waves with particles. For example, hitting the particles in case of fusion plasma. So I was wondering if all these incredible phenomena you have described to us on the wave side, if has been a study at what level, at what they do to the particles, because sometimes we use very boring pictures of what the waves do to move the particles under those fields. But if all these more interesting phenomena are taken into account, like caustics and all that, what will be the effect on particles?
Well, I chose light because I wanted phenomena that you could see with your eyes. But of course, you know, this is your question. I mean, in quantum mechanics, particles that are massive as well as photons also are waves, and you see caustics in other areas. You see them in an electron microscope. You see them in you see them in neutron optics, and phase singularities you see in I mentioned it very briefly in chaotic quantum dots. So these geometrical structures, which is a kind of complementary way of thinking about waves to the usual way you write down a wave equation, you solve it. You know that wave equations are similar, little differences, but similar for all different kinds of waves. Then a complementary way is to say, what are the singularities? Then you get into all this mathematics, and you get these pictorial ways of understanding what waves do at different levels. But they don't have to be waves of light. They can be, as I say, electron waves, for example, phase singularities. There were papers from theoretical chemists in the 1970s, about the same time as ours, seeing that in many waves describing, for example, chemical reactions, the electron waves would have these phase singularities, and you can't avoid them. So I don't know quite whether that's what you mean, but there is something else. Okay, so there's something else. Very commonly and understandably, a lot of the physics of light is from people who are using light to look at things. That's fine, it's wonderful. We do it, of course, with our eyes. But I'm talking here about light as a subject you study for itself. It's a curious thing that with electrons, nobody worries about electrons in materials. You'll understand the wave structure for its own sake. Of course, you do apply it in transistors and whatever, but still it's a legitimate subject in its own right. But somehow with light, there's this prejudice against zero mass particles that if you think you should only understand light in order to look at things, well, great that is, but here I'm speaking about how the laws of optics can express themselves in all possible ways. And the mathematics related to that is the theme of this particular talk. I don't know if that helps, but anyway. Malcolm.
This is a little bit probably far afield, but it just goes to your summing up. So increasingly people are talking about machine learning and all this kind of stuff. And so you're taking data, and then you're trying to figure out with the computer how to get more data, which is about things that you don't necessarily know, or there's a representation of it. But very often that representation on the inside of the machine has got little to do with the physics, the equations of physics, the things that you have been talking about. So at that point, what is the difference between, or is the theory that's on the inside of this machine still the same thing that we have spent all of this time, the history of humanity, forming the mathematical framework that we can understand it in the way that you do?
Just this morning, I had an email from the publisher of a journal that I'm on the editorial board of, and they're having a board meeting on Monday. I shall still be in the US, saying, should we have a section of our journal to do with machine learning, or should we create a separate journal? And so exactly this. Different levels of answering. I mean, part of your question is beyond machine learning. It's more general about what's the relation between the things in our heads and the things out there. Now, of course, that's a vast subject. Of course, physics is, of course, it's about the world. It's also about the way we interact with the world. You know, we live in a very narrow frequency range. We have limited concepts. I mentioned that at the end. But machine learning specifically, I didn't speak about it. I don't know much about it, but I'll tell you one thing. There are ways of seeing through misty objects, ground glass, for example. If you shine light through ground glass, you get a very complicated wave pattern. If you move the light source a little bit, that wave pattern moves around. But there are very particular illuminations related to the disordered structure, which you know about from electrons, where you do get rather sharp spots that you can use to illuminate things. And by machine learning, you can explore this whole landscape of possible illuminating beams. People do that. Art Lachendijk started it in the Netherlands, in Twente, in the Netherlands. And then you can devise ways of actually using completely disordered ground glass as a lens. And this involves machine learning. You can't, I mean, in principle, you could just look and do it by hand, but you can't, because you have to look at millions and millions and train the system to find these particular weird illuminating beams that make the glass act like a lens. So that's one example. It's slightly off my main theme, but it clearly will develop into a larger subject of its own, which is the origin of the question from my publisher this morning. Okay. This is another.
Yes, as you may or may not know, David Jessen from Cardiff spent some time here.
Yeah, good.
Right, and he was a co-developer with the Z-contrast atomic resolution microscopy.
Yes.
Microscope here, electron microscope. My question is with looking at these, in a sense, aspects of glasses and surfaces where you can see things that we almost can't perceive except when you take the second derivatives. Are they looking at this as for implications to technology? I mean, not only that, but are there applications that they think you could see that, or for forensics or something like that, or?
Well, it's a good question. I don't know. I mean, undoubtedly, I mean, of course, there are applications of everything. It needs a different kind of cleverness from the physicists who display the principles. David Jessen, you mentioned him. I mean, he saw my paper on the magic mirror, and he thought, well, this would be a useful way of a technique of understanding electron micrographs. So he's an electron microscopist. Now, we go back in the literature, there's some anticipation of it, but it's not. It gets clearer when you realize it's the Laplacian. That's right. So we started this project. With us, it's a kind of art-science project, really. And it's a kind of curious thing to make these objects to look like perfectly flat windows. When you shine light through, you get a picture that you would impress in a coded way on the picture. So we don't envisage application. But I did mention for the mirrors, as apparently in the semiconductor industry in Japan, this is a very, very effective way of finding little deficiencies, defects on the surface. I just make a point. I mean, I glibly said that the pattern on the back is reproduced on the front. But I wanted to actually see that and get with a surface profilometry. So I visited in David Jessen's department an astronomer called Peter Ade, who has a profilometer for testing the curvatures of lenses and mirrors in astronomy. So I thought, okay, he'll test this and he'll see these shapes. It took a long time, and the reason is you first have to take away, you have to, with software, you have to take away the curvature of it's a slightly convex mirror, but it's not a very good convex mirror, and you had to fit the surface with a 9th order polynomial before we could then see these little ridges that you see so directly by shining light on. Well, so with semiconductor surfaces, instead of zooming in with microscopes, you just, so this was their use of this ancient Han Dynasty 2,000-year-old technology, where these images were produced unintentionally, and therefore they were called magic, to look at semiconductor surfaces. So beyond that I can't say. I've no doubt there are, but we're not thinking about it. Oh, there is another thing. Yeah, let me just say that the parallels where you can see the undulations, these are people who work with architects, and the idea is to produce interesting windows in buildings which are curved, but where at certain points when the sun is, you'll see interesting things projected. So this is working with architects, and the people in Switzerland, in Lausanne, Mark Pauli and his people are doing that. Okay, so that's an application. Yeah, there you are. You must be careful because, I don't know if you saw it in the news a couple of years ago, a new building in London, the windows weren't perfectly flat, and in the sunshine, those windows produced caustics, and they melted the plastic on a very expensive car below. No, it's very interesting. So you know, they had to refigure these windows to stop this happening. The word caustic comes from the Greek word for burning, so it's literal in that case.
Any further questions? Well, the thing that impressed me is you have an amazing body of work, but I think that the thing that I took away from this is that you're having an awful lot of fun, which is something that all scientists need to have in their life, right?
Well, what's the point otherwise?
That's right. That's right. But I really appreciate you coming, and like to have everybody thank him for his excellent lecture.